In this video, we shall look at a couple of review problems associated with magnetic force on current-carrying conductors. First, a brief introduction. Let's assume you have a current-carrying conductor as shown. This conductor carries a current, say I. The length of this conductor is L. Assume that this conductor is placed in a region where there is a magnetic field directed in that direction. An electric current is flow of positive charges, in this case to the right. As we have seen before, a magnetic field can interact with charges and exert a magnetic force on these charges. So that means this magnetic field will interact with that electric current and exert magnetic force on this conductor, which carries the current. The magnetic force is given by the following equation. It is the current in ampere times the cross product of two vectors, namely the first vector is vector L and the second vector is the magnetic field vector. So how do we define the length vector here? The length vector here refers to the length of this conductor, so the magnitude of that length vector is the length of that conductor itself. The direction of this length vector is the same as the direction of the electric current. So if we assume that the conductor and the magnetic field lie on the same plane, let's call that plane the xy plane, then using the right-hand rule, when you curl from the length vector, in this case the x-axis, to the magnetic field, which lies, let's say, on the xy plane in that direction, then as a result of that right-hand curl, the direction of the magnetic force is the direction of your thumb, the right-hand thumb, and that is the direction of the magnetic force, namely along the direction of the positive z-axis. Another thing to note, the magnitude of this magnetic force is quite simply I times the length of the conductor times the magnitude of the magnetic field times the sine of the angle between the length vector and the magnetic field vector. In this case, that's the angle. So what that means is, if the direction of the magnetic field is parallel to the direction of the current, then we see that alpha is 0 degrees, so there is no magnetic force exerted by this magnetic field on this conductor. Likewise, if the magnetic field is in a direction anti-parallel to the direction of the current, then the angle is 180 degrees, and since sine 180 is 0, there will not be any magnetic force exerted by this magnetic field on that conductor either. Now let's get to the problems. A rod of mass 0.75 kg, so that is the rod in green, and the radius of the rod is 6 centimeters, rests on two parallel rails that are 10 cm apart. So this is one rail and this is one rail. The distance between them is d, that is equivalent to 10 cm. Another thing to note is that you can view this rod as a cylinder, and it's rolling like that. Capital L is 45 cm in length. The rod carries a current of 50 ampere in that direction, namely that direction. And the rod will roll along the rails without slipping. A uniform magnetic field with magnitude 0.25 Tesla, that's that, is directed perpendicularly to the rod and the rails. If the rod starts from rest, find the speed of the rod as it leaves the rail, which means when the rod gets to that position, what is the speed of that rod? Let's try to understand what's going on. So you have a current here, the field is going upward, so that means there is a magnetic force acting on this rod. That magnetic force is given by the following cross product, I the length vector, in this case you can take that to be d, cross into a magnetic field. The direction of that length vector is the same as the direction of the current, so it's going that way. The direction of the field is perpendicularly up. So when you make your cross product with your right hand and you curl your right hand fingers from the direction of the current to the direction of the magnetic field, you see that your direction of your right hand thumb is rightward. So that is the direction of that magnetic force. So this magnetic force will start to push that rod all the way from rest up until the end of the rail, at the point of which it would be moving with some speed v. We want to determine that v. What we need to apply is the work-kinetic energy theorem here. The work is work done by this magnetic force on this rod as it moves a length capital L. So that is F times L, and this work by the magnetic force equals the change in the kinetic energy of the rod. The final kinetic energy, namely the kinetic energy of the rod when the rod is at the end of the rail, minus the initial kinetic energy, namely the kinetic energy at the beginning. We know it starts from rest, so it does not have any initial kinetic energy. So let's write down the left-hand side of this equation. The magnetic force is given by current times the length of the rod times the magnitude of the magnetic field. The direction of the current and the magnetic field is perpendicular to each other, so sine 90 is 1. The distance the rod travels is capital L. Now let's work out the right-hand side. The kinetic energy of that rolling rod. The kinetic energy is of two kinds. One is the translational kinetic energy, and that's given by half times the mass of the rod times the linear speed squared. This is the speed that we want to determine, namely the speed of the rod when it is there. We also note the rod is rolling about its center, so there also should be a rotational kinetic energy, and it's given by half times its moment of inertia of that rod, which we can model as a cylinder, times the square of its angular speed. The moment of inertia of a cylinder is half times the mass of the rod times the square of its radius. And don't forget omega. Omega is given in terms of this linear speed as the linear or the tangential speed of the rod over the radius of that rod. So v squared over r squared. And this r squared will cancel that r squared. So the right-hand side of that work energy theorem is half mv squared plus half mv squared. And that is just 3/4 mv squared. So let's put that on the right-hand side, 3/4 mv squared. Now let's put all the numbers in. The current is 50 ampere, so that's I. D is given to be 10 cm, so let's convert that into meter, 0.1 meter. B, the magnitude of the magnetic field, is 0.25 Tesla, that's given there. And capital L is 45 cm, so 0.45 meter. The right-hand side, 3/4. The mass of the rod is 0.75 kg v squared. And you can solve for the v. And when you solve for v, you get 1 meter per second. And that solves the problem. Problem 2. The circuit below consists of wires at the top and bottom and identical metal springs in the left and right hand side. So those are metal springs. The upper portion of the circuit is fixed. So that is the upper portion, and that is fixed. The wire at the bottom has a mass of 15 grams and 7 centimeters in length. So that is the wire shown in green. The spring stretches 0.8 centimeters under the weight of the wire itself, and the total resistance of the circuit is 13 ohm. When a magnetic field is switched on, the springs stretch an additional 0.5 cm. Find the magnitude of the magnetic field. We note that the direction of this magnetic field here is coming out of the board. The resistance to this circuit is contributed by that resistor itself, and all the other parts of the circuit is assumed to be of zero resistance. The EMF of the battery is 26 volts, so the current goes like that, from the positive terminal of the battery to the negative terminal of the battery. So throughout that bottom wire, the direction of the current is rightward, and it completes the circuit like that. Let's first determine the magnitude of the current. According to Ohm's law, it is the EMF 26 volt over the total resistance of the circuit, 13 ohm, and that is 2 ampere. Now let's concentrate on the point. The springs stretch 0.8 cm under the weight of the wire itself. So before you switch on the magnetic field, this wire would cause the springs to stretch 0.8 cm. That information would enable us to determine the spring constants of these two springs. They are identical. So let's apply the free body diagram on one of the springs. So you have the stretching caused by the weight of the wire. So the weight of the wire is mg. The stretch is given by, according to Hooke's law, K times the amount of stretch. The mass of the wire is 15 grams, so 0.015 kg. G is 9.81, the acceleration due to gravity. K we don't know, and the stretch is 0.8 centimeters. So 0.8 divided by 100 to convert that into meter. And you see the spring constant can be worked out. In doing the calculation, you get 18.4 Newton per meter for the spring constant. Now, when you switch on the magnetic field, the springs stretch an additional 0.5 cm due to the magnetic force. Let's work out the direction of the force. This is the direction of the length factor, namely the direction of the current. The magnetic field is coming out of the board. When you curl your right-hand fingers from the direction of the electric current to the direction of the magnetic field, you see the magnetic force is going downward, because that would be the direction of your right-hand thumb. So magnetic force is downward, and that will cause an additional stretch of 0.5 cm. So what we have is the magnetic force, which is given by I times the length of the bottom wire times the magnitude of the magnetic field, equals K times 0.5 over 100. So 0.5 cm converted into meter. So the right-hand side is the force due to Hooke's law. Substituting the numbers, current is 2 ampere. The length of that bottom wire is 7 cm, so 7 over 100 meters. B is what we want to find. K, spring constant, has been determined, 18.4 Newton per meter. And the stretch, the new stretch that is 0.5 over 100 in the unit of meters. And you can solve for the magnitude of the magnetic field, which turns out to be 0.657 Tesla. And that solves the problem. If you have any questions, please leave them in the comment section, and I'll try my best to answer them. As always, thank you for watching.